Okay, so thank you very much for having me here. It's wonderful to be back at CERM. I was just thinking that the first time I was here, I was about the same age as, I was a grad student myself, so things have changed a lot. I've changed a lot. Time has gone by. And so I have a number of things I want to talk about, but I really want to take the opportunity, since there are so many students here, to just sort of give some overview of different kinds of things. So the abstract is promised is changed quite a bit, really. But I want to touch on a few things along the way. So let's see. So I want to just first of all advertise that there's a new edition of this book, The Symmetries of Things, coming out in 2024. This was co-authored with John Conway, who, of course, the senior author is no longer with us. But it's going to be a very short book that's, if you know the book, it's going to be much shorter and more geared towards the general public. But just to give you the theme of the book, if you haven't realized, since this is a very topologically minded audience, we want to we really want to get rid of the old crystallographic notation and replace it with something more meaningful and appropriate for the 21st century, seriously. And so the idea of the book is just simply that you can understand, in general, you can understand geometric group actions by their quotients. Well, that's not true, because in 3 dimensions, you're already stuck with things like the Poincare conjecture. And of course, in 2003, that was solved, but that's really hard. In 2 dimensions, it turns out to be really simple, really great, very powerful way to understand wallpaper groups by their quotients under the group. So the thing these little folded up surfaces are just simply that thing, but where we mod out by points that are equivalent. And that's it. So you can use things like Euler characteristic. And really, I'm just pointing this out partly to put myself on the hook that this is coming out, and partly I want you all to buy it. The real question that I want to address, which I think really underlies a lot of my interest in this work, and I think perhaps many of you, is just simply this: like, when shapes fit together, what can they do? And that may be that's sort of like that's a very broad question that plays across all over the place, but it's not just recreational. I mean, so all around us we have this kind of phenomenon where little tiny gadgets assemble to produce wildly complex things. So just to take a really grandiose example, just proteins. Or we could go back further and just take atoms. Atoms, we are made up of atoms. We're made that assemble into proteins. Proteins are very complicated combinatorial gadgets that basically work by the way that they fit together. And yet we can see that that gives rise to us, so that's pretty complicated. And then here's a cool little thing. This is some sort of plankton, but here you can really see that it's assembled out of these, it's self-assembled out of these little plates that somehow form these things and form that, and that's pretty cool. Last summer I was, on the basis of just this new notoriety, I guess, I got to go to a conference with a bunch of physicists and chemists and so forth, looking at just simple packing questions that, believe it or not, and I know this might seem hard to believe, but as mathematicians we know how hard these things are. This is literally state of the art in terms of what they're interested in, is just how do you fill up, what are the possibilities for how spheres could fit in a cylinder. I mean, it's like 2024 now, and this is where the experimental sciences are. And I mean, I'm sorry, it's true. I mean, I guess so here that works a little better. Like, you know, with them I have to be more careful what I say. But like this is beyond the state of the art. Like, what is that? That's actually from a deli near my home. But also I do this just as an aside, because I originally was asked to give a presentation on math and art, because that's something I am very involved with in other kinds of ways, other settings. But it does sort of have this feel of fitting things together. So one of the things that I do, or have done a lot of in the past, is what I call participation art sculpture, where the goal is really to design something that's neat, but then also the process by which it's assembled. And so this is one from quite a while ago that produces this thing with this very unusual, very interesting space symmetry. This is hard to understand looking at it. That's why it's compelling to me, but it's perfectly symmetrical in the infinite abstract thing. Or here's another one that's kind of fun. I guess it's an open problem. It's kind of seems like it would suit the people, many of you here, to answer this question. On some levels it's very easy, but I'll explain the subtlety. It's just simply, here we have, and I had to go to 2 different hardware stores to get enough of this stuff. It's this thing goes through each 1/8 of the cube once, and then it goes through each 1/8 of the 8th cube once, and we can do this at different levels. So this is the next level up, where again people were assembling these pieces and we get to this thing. So this is 512, it's 1/8 of 1/8 of 1/8. And the 1 of n thing is it's actually pretty easy to write down how many strings of 512 pipes there might be inside of a cube. The little bit trickier is to deal with the end conditions. And that's where, and then also to mod out by symmetry. So that's why I don't actually know the answer to the question of what the actual name of the sculpture is. So, and then here's another one. This is the gyroid, which is a famous minimal surface. And I like this one a lot. And here's another one. This is a bit of hyperbolic geometry. This is literally, I mean, it's literally a surface of, well, no, it isn't, is it? It would be if you could fill out the surface a surface of constant negative curvature. And what I really want to emphasize, especially with mathematicians, is that and this was sort of the other talk that I'm not giving, is that the mathematical ideas can be embodied in physical reality, and moreover can force physical reality. Physical reality has to conform to the mathematics. So these yellow things are truly geodesics, and they have to be. They don't have to be because this was calculated. They have to be because they're straight strips of steel, and and you simply can't bend. You can only bend steel in the normal direction. So these necessarily are geodesics. And then, by the way, this is another one which is right here. So this will actually make an appearance in the talk a little while from now. But this is particularly cool stuff and fun to play with. And I actually have so this is also a piece of the hyperbolic plane. This is constant negative curvature. And then what I've got sort of floating around here, I can point with the laser pointer there, is that during lunch I would like to build, I have a new way of building a Klein quartic. This is not like any picture you've seen of the Klein quartic before, because it's a new picture of the Klein quartic. So a Klein quartic is, of course, or maybe many of you don't, I mean, I've been asking around, so it doesn't seem to be widely remembered, but the Klein quartic is a genus 3 surface that has this very rich symmetries. It's basically a Platonic polyhedron, but with on a higher genus surface. So anyway, that's that. So the general context. Oh, and just to go back to other ways that gadgets can fit together. Within mathematics, of course, we've seen endless examples, but let's remind ourselves that even logical fragments have this property, that logical fragments are just logical symbols are just things that fit together by local rules, and there's even local rules for determining, when one logical statement, formal statement, can be followed by another one, and so on. And so already we can see that essentially this question is so broad to be sort of meaningless, I suppose, on one end, because it encompasses all of math, so it's too broad. But very compelling. So in any case, you might have heard about this. This is the first known aperiodic monotile, which I'll define shortly. And what's even more remarkable, and really is remarkable, is that it's just one of a continuum of such. But then it's like the gift that just didn't stop giving. It was actually also, there was something, the previous one, these require reflected copies of the same tile, which I'll address later. But then amazingly, this one, if we don't allow reflections, is still aperiodic. So this was quite remarkable, and I'll touch on that. And then I guess, I don't know, I mean, I imagine many of you have heard about this. So immediately there was this crazy, overwhelming response and from social media and other places, and people making this their own. It's really kind of really, from some perspective, really extraordinary. I've never been involved with anything like it, of course, and never expect to be again. And the internet promptly told us that it was not a hat, it was a shirt, and of course it is. And and so we saw this incredible outpouring of work. So these are some of my favorites. Most of them were a little more innocent than the tattoo, beard, and soccer hooligans. But nonetheless, we have these wonderful examples of people. Now this one's interesting too, because this has kind of a connection to the symmetries of things, in a sense that there's a periodic tiling that involves hexagons, and just the clever idea is by replacing those with pentagons, you can make a spherical pattern. But just as another little, yes?
And there seems to be a torus or a cylinder there. So
oh,
is that a valid tiling?
Oh, that's actually a great point. So, A, there's actually a seam in the back of the can. But B, it's a theorem which has sort of been kind of invisible. Like, it didn't actually occur to anybody to state it, but the proof is already 30 years old without the theorem, if that makes no sense, but it's true. But it appeared in another context in a more general form, that any set of tiles that admits any set of tiles that's aperiodic, where the tiles appear in only finitely many orientations, so ruling out but even the pinwheel it applies to, then for any width, you can find a periodic strip of that width. So it doesn't tell you what the length is, but being able to form cans of these things is actually something that's true of all tiles that can form a tile in, whether or not they are periodic.
So the discrete version of that has definitely been stated, but maybe not the continuous one. But okay.
Okay, well, I'll talk about that, yeah. It just sort of never even occurred up to me until this year. And then this one's from the library. You can't see that, but of course it says CERM. That's kind of fun. And then just as another little thing, I'd like to share this. So on the basis of the incredible response, MoMath, where I work now, and the United Kingdom Mathematics Trust sponsored this, more to the point, these wealthy people sponsored this contest with real money behind it, and we got some amazing entries. These are just some of the winners. So this is a kite made of a hat shape, made of kites, made of hats, and of course the hats themselves are made of kites on a finer level, so that was pretty cool. And so Debbie's a high school student. And then this one was just so whimsical that it won. So this was some ravioli, and then this was just another piece of art. But there were so many interesting things. So we had a lot of food. We had a lot of inedible looking food, but a lot of pretty good looking stuff, including that's weird. It's not updating on this. That's strange. I don't know what's going on. Okay, so including this beautiful dumpling and tremendous number of quilts, beautiful, all sorts of clothing, a beautiful jacket, isn't it? And then lovely, what's weird, a knitted sweater. And then this is by a child, but I really like that this one is, she paid attention to the fact that the orientations of the kites matter, which they do. And then this is hand painted. And this is hand painted, but it's still impressive, but not the same. And of course we saw lots and lots of these sorts of things, puzzles, decorated puzzles. This one is really extraordinary. So we got a lot of ideas for pixelating things, and somebody wrote a piece of software to do this with images, but this one is just really something else. So this is a little TV. I don't know if you... Isn't that awesome? I guess it's not coming through on the screen. And then this one was really, really fantastic, but I was a little disappointed that the bubbles still came out spheres. So that was... And then of course there was some mathematical response, a lot of mathematical response. So a couple of notable ones is that all the cohomology stuff from the last 20 years or so was, of course, and cut and project stuff, all of that was cleaned up within about a month, I think. And then similarly also the diffraction patterns and so forth were computed. And there's lots and lots of stuff. but these are some of my favorites, and I'll come to this later. So the question really is, what's this all about? And so my real theme here is, again, to return to the complexity of tiling questions and to put some things in context. And so some of the things that Nicholas Ollinger talked about in the last hour will be, I'll be repeating basically in some ways. And so hopefully that'll help reinforce it and make it clear. So what is an aperiodic monotile? So the basic question here, which is really kind of amazingly subtle, is just simply, can copies of this shape be formed to, well, this one's not pretty subtle. I think all of you, I think all of you know the answer to this one, don't you? So can this one be used to form, copies of this be used to form a tiling? And of course, that's moronically simple. But and this one, I think you can all pretty well come up with a proof very quickly that it does not admit a tiling, because, so a monotile is a word that has come into fashion very, I don't know how old it is, but I think it's, so far as I'm aware, it's a fairly new term. Maybe somebody could contradict me on that. But the monotile is just simply defined to be a tile, which requires some definition, that can be used to form an infinite tiling of the plane. That is to say, a partition of the plane, I mean, not quite, a covering of the plane where the tiles, copies of the tiles have disjoint interiors, and there are no, and it's covering. So a tile, I should say, is kind of a problematic term. And so what we might mean just simply as a closed topological disk is the simplest possible thing. But I've come to start using the word shape, just because tile is sort of, by the time you make tile precise, you've loaded it up with so many words that shape is appropriately vague, frankly. So how can we tell? So here's another example. Oh, well, what's the proof for this one? It's just simply that one proof might be if you take the point, something has to fit there, and the only thing that's going to fit there is a point. And by this time you stick a point in there, you've pretty much blocked off any other possibility of filling that in. So that's the end of the proof. Here's an example from Casey Mann in 2006. This one we can certainly prove does not tile the plane. This is in fact the largest configuration that it can tile. It has a central tile and then a complete ring around it and a complete ring around that and a complete ring around that. We might say that this has combinatorial radius 3. It has radius 3, but in what sense? Well, in some sort of combinatorial sense it has radius 3. So why would it not have any further possibility of going any further? Well, the 3-ness is hard to answer, because that takes brute force to be sure of it. But the basic idea that this cannot tile the plane is pretty straightforward. So this is made up of 4 hexagons, of course, and it has 4 outs and 7 ins. And in any completed patch, in the interior of any completed region that's been covered, each out will have to match an in, right? And of course there's an imbalance. Every individual tile introduces 4 new mismatched of those. And so all of these mismatches have to be on the boundary of the patch. So all of these match, so all the mismatches have to be on the outside. But that's a problem, because basically the number of tiles is of course growing by area, which is roughly the square of the radius. And the length of the boundary is growing by roughly the radius. Now, of course, when I say roughly, that's masking a lot of wiggles and a lot of initial conditions kind of things. But it's obviously of the order n squared, order r squared, order r. And so, of course, every order r squared eventually beats every r, order r. And so eventually the boundary is just not enough room for the, I see that my slides are a little long for this screen, so there might be some other cutoff things. But eventually there's just simply no room. So that's an argument. And this, so we call this tile, we say that this tile has H number 3. The H number is simply, for a tile that doesn't form an infinite tiling, the H number is simply the combinatorial radius out to which you can, yes, Julian?
Is there a problem with the green that touches the light green?
Uh-oh.
Brown in the middle?
Here?
Second,
Did I make a mistake?
green does not
Oh, maybe I made a mistake in the drawing or something? I don't know. Undoubtedly you're right, but let me look at it afterwards. If there's such a mistake, it's obviously in the drawing, not the result. So anyway, right now in the state of, in 2024, this is the world record, which is just 6. And that's it. Okay, that just means, but this is, plenty of people have looked at this, and the question would be, are these H numbers unbounded? As we'll see, this is much like the question of looking for busy beavers, if you know something about that. We're looking for tiles that would be able to do so much and go and go and go, and then all of a sudden crash. And, well, okay. Now, this one, I think so highly of this one that I would like to maybe pass out some, maybe I could have some help so I can come back up here. But I think you should, I'd like to just distribute these. You can, here, maybe I could just take some and pass the bag back and send some of that this way. I'll take a few this. So, and as you get your hands on these, you might ask what you can do with them. And so when you do this, you will find very quickly that you don't know. So as you start playing with these guys, you'll see this is sort of out of focus, so I'm not going to worry about this too much. I'm going to give you the answer anyway in a moment. But as you fit these together, you see that they have this kind of fantastic array of combinatorial possibilities. And it's not really at all going to be clear as you play with these what's going on. In fact, if you disagree, I'd really like to hear about it. So hopefully this will come back on. If not, I'll just stand over here and show you some other tiles and okay, good. Okay, so more generally the question is, how can you tell? I guess some of you obviously many of you in the back are not going to get tiles, so why don't I instead send this bag back to the rows that didn't get, they can have hats. So, this tile is by Joseph Myers in 2003, and it was found by extensive computer search. And the question is, what would be an algorithm to even tell if this tile is the plane? And I'll come to that algorithm in just a moment, and it's actually the algorithm that was used. But what's remarkable about this one is that this is the simplest thing it can do. The simplest, it can form a tiling, and it can form periodic tilings. But the simplest tiling it can form is this one. The simplest periodic tiling is this one. Notice that it has this is a fundamental domain. This region can be replicated. It's rotated by 180 degrees somehow, and I can't really quite see it from where I'm standing. But this chunk is rotated by 180 degrees and then translated around. So this is the smallest possible, the simplest thing it can do. And there's a measure of how simple this is. So if a tile tiles periodically, the isohedral number is the smallest fundamental domain that it admits. And again, this is kind of like a busy beaver-esque type question. This is, in fact, this also leads us to another. Is isohedral number unbounded? Is it, for any n, is there some set of tiles that does tile periodically, and yet the smallest fundamental domain is bigger than that, n? And then this is another lovely example from the same computer search of an isohedral number 9 tile. And I should say both of these are the world records at the moment.
Sorry?
Yes?
Is it the case that if you assemble some, then you can always continue a tiling and extend it to the plane?
Do you mean if you put them down at all, that you can always extend?
Yes.
Probably not, but I don't know. I would imagine not, but I don't know. I don't know that for sure, but I'm almost certain that that's because I'm sure you can get stuck. You can probably get stuck immediately if you try. Getting stuck is easy, yeah. So that's easy. Okay, so the question is, and more generally, and this is what Nicholas had been talking about, is there an algorithm to determine whether or not, well, this is a more specific one. So is there an algorithm to determine whether a given tile is a monotile? And I'll come to this in a moment, but as Nicholas pointed out, the so-called completion problem is undecidable. And let me just describe this. So if you have a set of tiles and a starting configuration, and you ask, can the configuration be completed? So the more general question than you were asking there, it's simply undecidable. And this is the same exact thing that he gave in his proof. Sorry, if you have a set of tiles. So this is the same exact idea, it's the same exact proof. It's that if you start with a Turing machine, which just to sort of go to the trouble of saying what that is, it's given by a transition table. We have a list of symbols that are our states and a list of symbols that's the alphabet. We're on an infinite tape, and at every moment the machine is at the head is at a given state, at a given position, and then determined what it reads. B0 tells instructions to write a 1 on the tape and move to the left and go into state A. So B, we write a 1 on the tape, move to the left and go into state A. And if we ever reach this special, like there might be some state that just has no transition, some halt state, in which case that's it. And so famously, of course, there's no decision procedure to determine if we ever reach this halt state. And so this is the point that just exactly as was described in the last lecture, we can view this as a picture. We can view this picture as a tiling. This is essentially the same picture as before, but now I've chopped it up into little squares. And the little squares have matching rules, exactly as described before, that are more or less what has to happen. So if I'm here, I was reading a B in state 0, that tells me I have to go to the left, go into state A, and having a written 1 there. So this pair of tiles here exactly captures what happens when you're reading a B in state 0, reading a 0 in state B, and you're next to a 0. That's completely captured here. And then whether or not this is a legitimate run of the machine is completely encoded by what fit together. So this is also from the last lecture. But the problem is that, so this tells us that we can form a tiling if and only if the machine doesn't halt, but we can't decide if the machine halts, so we can't tell if we can extend this to a whole tiling. But the problem is that we can also tile with just the blank tile. So it is certainly decidable whether or not a set of tiles like these does or does not admit a tiling. The answer is yes, and it's just use that one by itself. So the much more subtly is, can you somehow force this to happen? And I'll touch on that just as Nicholas did. But let me talk about the obvious algorithm to determine. The obvious algorithm to try is just to simply list larger and larger patches, to enumerate larger and larger regions. And what will that accomplish? If you enumerate larger and larger patches, you'll eventually discover if a tile does not admit a tiling. And this is a little subtle, but it was also addressed in the last lecture in a little bit different context. But it was the same as showing that where's Nicholas? You did something with Koenig's lemma. I've forgotten. You were showing that cellular automata have limits. Yeah, that the cellular automata are compact. It's this exact same idea. So the idea is that, so if a tile does not admit a tiling, then there has to be some size disk that it can't cover. You can imagine that if it could cover larger and larger disks, then if it could cover larger and larger disks, then it could cover the whole plane. That sounds obvious. It isn't quite, and the proof was essentially given in the last lecture. But it sounds obvious, and going with that. So if you can enumerate, if you eventually find larger and larger patches, then you can find a tiling of the plane. Conversely, contrapositively, if you can't have, there's no tiling of the plane, you'll eventually run out of some size patch that you can form. And so just as an aside, this is related to H number, because if H number had a computable bound, or had a bound specifically, but a then we could just do this. We could just enumerate patches until we reach that bound, and then we're either home free, we know there's no further problems, or not. So a monotile is, a tile is aperiodic if it cannot form periodic tilings. And if there were no such thing as an aperiodic monotile, then we'd have a decision process. We would just simply we would simply enumerate all patches. Hang on, hang on a second. Something seems to be missing from this. I beg your pardon. I think I'm missing a slide here. I'm sorry about that. So anyway, the point is that, so maybe not. So anyway, the point is that if a tile does not, let's see, if a tile, we can also check to see if we have, as we enumerate patches, we can also check to see if we have a periodic tiling. That's also decidable in this way. So we can check to see, if it does not admit a tiling, we will find that out. Similarly, if we enumerate patches, we can check to see if we have a fundamental domain. We just sort of go around the boundary and see if that chunk can fit together with itself. So if a tile admits a periodic tiling, we will find that out. What could go wrong? What could go wrong is that those procedures don't halt. How could they go forever? The only way they could go forever is if we enumerate larger and larger patches, and yet we don't ever find a periodic tiling. So the only thing that could go wrong is that if there were an aperiodic set of tiles. And so that's the fundamental connection between these things. And so to give a second Wang quote for the day from the same paper, but just a little later in the same paper, here's the so-called fundamental conjecture. Now this is called the domino problem. A finite set of plates is solvable. Well, now that means we would say a set of Wang tiles, a set of squares as in the last lecture, admits a tiling if and only if there exists a cyclic rectangle. Well, if and only if there admits a fundamental domain. And so so basically he's just pointing out what I just said. So if every set of tiles admitted a periodic tiling or no tiling, then we would have a decision procedure for the domino problem. And as I'll mention a little bit more, but was touched on last time, is that if there's more than one kind of tile, then there's no method to determine whether a set of tiles forms a tiling. And I'll mention that in a minute again, but basically a finite version of this, a real world version of this, is that there's all kinds of ways that this shows up. And so one way is these puzzles that you might have seen, where this is actually a really, really hard puzzle, because essentially these are, well, for 3 by 3 it's not NP complete, it's just a finite chunk of tiles, but asymptotically this is an NP complete problem. So it's NP hard. It's NP complete and it's NP hard. So we have these implications. If the monotiling problem, if a single tile is not, if it's undecidable whether a single tile admits a tiling, then this would imply the existence of an aperiodic monotile, and similarly the H number would be unbounded. Of course, we know that's still open, and then as we'll see momentarily, of course, this has now been decided, figured out. And then we also have the same kind of thing, the monotile period problem. That is to say, if a tile admits a periodic tiling, is related in this way, it also would imply the existence of an aperiodic monotile and that the isohedral number is unbounded. So these are all just more or less consequences of the things I was addressing. And this is the status here. So these are all open. Now, I'm going to just quickly race through a few ideas here because I only have a little while. But the point is that this is a very general framework, which I think has been pretty productive for the last 25 years. I mean, a lot of interesting work has come out from basically, not necessarily explicitly in this framework, but fits nicely into it, of just sort of looking at these related questions, which I'm not going to go into detail about them, but you can see some relationship. We have this word weakly and strongly, which is kind of technical, but we can ask this in any kind of a place that we like. And so we can ask which of these might work. And for example, for sets of tiles in the plane, this is the long-standing results of Berger, and then just some modifications of that, I guess in kind of an obscure place, but nonetheless, this has appeared in other places since. So where each of these is now known to be true if we allow multiple kinds of tiles. And a number of people here have contributed to that. So Nicholas, for example, has shown that, for example, 5 polyominoes is sufficient to get the undecidability going. So again, a monotile is aperiodic if it can't form periodic tilings. And in the specific, that seems like a duplicate. Okay, never mind. So we have for translations, none of this holds. We have recent work by Greenfield and Tao showing this, more or less, this is the state of affairs for the plane where we cross it with a group, a finite group. We have, in the hyperbolic plane, we have a number of interesting results. So a weakly aperiodic protoset is this guy, and it's here. This is it. So these guys, you just chop these up into more or less, you know, each tooth gets its own tile. And this is a non-periodic tile, would be a non-periodic tiling of the hyperbolic plane, which is pretty cool. I mean, I can hold it. I love this. And that's another thing, again, I want to just stress to all of you young mathematicians, is that you don't have to do it all abstractly. You can hold this stuff. I'm serious. That's probably the most important thing I have to tell you. So here, let me just pass that around. So that's, this is non-periodic because if it's the same kind of imbalancing argument. Each one of these guys has 2 teeth out and 1 tooth in, and so they all have to match, but I can never have a compact surface. There's no compact quotient by any kind of group action here because that compact surface would have to be covered with a finite number of these guys, but then we would have twice as many outs as in. That doesn't make any sense. So it's either 0 or infinite, basically. And then we also have the completion problem is undecidable. That's essentially the same proof. It's essentially trivial. And then we have a whole bunch of other results. So I gave those. Other people gave those. Carey and Morgenstern proved that's undecidable, and then that. And we have those open. And then next week we'll hear a lot about subshifts of finite type on groups, which has been a very active field that a great number of people here have participated in and pushed forward, and there's a lot of stuff there. And I'm sort of hesitant to say too much because I'll probably piss somebody off. But because there's so much, there's so many things. So next week I think we'll hear a bunch about this. And I just want to advertise a couple of results. Oh, so of course we have the same setup. This is the same questions as before, just now changing the definitions a little bit to suit this other area. So this is essentially the domino problem. This is essentially existence of a aperiodic set of tiles. And this, that may be, that, oh wait, sorry, that's the domino problem. And then this is a little technical. And then I just want to advertise a couple of results. So one thing that's really important is that these questions are invariant under quasi-isometry. So that sort of really establishes that it's not about the group graph. It's about the group, and it's not even about the group, it's about the general shape of the group. And so just to give a sense of the kinds of results that I'm more invested in. So all one-ended hyperbolic groups have one of these guys, and then very recently Bartoldi proved that the emptiness problem is undecidable. So I'm really going to have to race a little bit and I have to sort of decide what I want to show you, but I want to just sort of show you a little bit about the history and this hierarchical method. So I should add, but because of this underlying undecidability, what we know about the ways of proving things are undecidable is necessarily essentially like measure 0 of the possibilities in some sense. I mean, that's sort of a broad statement about any kind of situation. Working with decidability questions, you're sort of guaranteed life employment in some sense, and that we'll never really get to the bottom of any of it, right? But nonetheless, this has been a very productive point of view that has provided just tremendously valuable over the last 60 years now. And so just to take this example, this L tile is not an aperiodic monotile by any means. Here's a periodic tiling, but it can be used to form hierarchical tilings in the following sense. We have an inflation and subdivision rule, and it's not, again, it's actually non-trivial that this would imply the existence of tilings that would have some sort of structure, but you can believe it by building larger and larger patches. We can assemble tilings, and it's true. And these have the property that any given tile would, in this case, each L appears in a larger L, in terms, some larger L and some larger L still, and ad infinitum. And that's true of any given L. This one is in this chunk, is in this chunk, and so on. And moreover, every L is in a unique such hierarchy of L's. That's the key. So every tile is in a unique hierarchy of larger and larger, what we call super tiles. And so such tilings are necessarily non-periodic. And the reason that they're non-periodic is that even if we don't have the markings that show the hierarchy, we can always recover it. The hierarchy is always there. And if there were some translation, okay, suppose there's a translation that leaves this thing invariant. Just suppose. Well, what's going to happen? There's some supertile that's larger than that translation, but I just said that the hypothesis that every individual tile lies in a unique hierarchy of this. So in particular, if I had that translation, I've already blown it, because see, like that tile there, to pick one, is in two different infinite hierarchies. It's in two different supertiles of this size. It's in this one, and it's in this one. And moreover, they have the whole hierarchies after that. So that's a contradiction. Again, every tile lies in a unique such hierarchy. And you can see there's problems. Like in this example, there's some mess here, and that's necessarily so. That mess has to be there. So hierarchical tilings of this kind are necessarily non-periodic. And here's a cool little video. It's kind of fun. That's too fast, so I just want to show, if I can find, you can get it to line up pretty good, but you can never get it to line up everywhere. You can do pretty well. And of course, you can get within epsilon of the whole plane, of the measure of the whole plane. Okay, so, but then there's this business, so that's not an aperiodic monotile, but these guys are, and the proof that they are is a little complicated, but basically it comes down to a combinatorial check. This is much like the example that Nicholas gave, where these guys fit together, and they have to form these larger and larger structures. And I don't have the slide prepared, but if we had the slide prepared, you could see that there's sort of an underlying L tiling underneath it. This is much like a picture that was shown in the last. So these little guys, these two tiles, these two shapes, for whatever reason, can only form basically what is the original L tiling. And what do I mean by the same? Well, there's some sort of notion of converting this tiling to, like erasing the markings basically, and recovering this underlying L structure. And in that sense, so the underlying L structure can never be periodic, then neither can this be. And this is the same, I'll skip this, but basically this is the same idea that Nicholas was saying, is that you can use this hierarchical structure to encode Berger's result. And this seems to be a messed up slide, but it's giving little sandboxes on which to run the simulation. And of course, there's been many, many things found since. The Penrose tiles were, I don't know, it seems presumptuous to say were the most famous. Maybe they still are, but they're certainly up until last year, they were indisputably the most famous example of this. And I hope you've all seen those and played with them. And here we have the hierarchical structure of, these sort of pentagonal structures, and then larger pentagonal structures, and larger still, and so on. And then Aman, who is a remarkable person who showed up in a number of ways in this subject, gave this one. And I'd just like to mention that there's no real theory of substitution tilings, though there's really an astonishing variety of them. And I want to return to this point that there's, again, a real lack of theory of what can be where you take shapes and you replace them with larger copies of themselves that are subdivided, and then iterate this process. When I say there's no theory of, there's substitution tilings as a thing are understood once the rules are presented to you, but a theory of what rules are possible in the first place remains to be seen. But we do have, these results. So this is really three separate things. There's a Moses, myself, and Fernica Nollinger, and then the differences are all here in the asterisk. So for every tiling substitution rule, there's a set of marked tiles that would then do the same kind of business. This asterisk is holding a lot of stuff that I'm not going to go into right now. Experts know. But just to give you an example, like here's a so-called Sphinx substitution rule where you have this weird shape called the Sphinx. It can be replaced with 4 copies of itself. And this crazy collection of tiles would then enforce the Sphinx. And this was constructed just by turning a crank. All three of these proofs are constructive, and so just sort of turning a crank in the machine. And so the natural question, obviously, is can a single tile suffice? So about 45 minutes into the talk, I get to the hat. Now, one thing I should say, too, is this word Einstein. So I apologize. It's not my fault. Ludwig Donzer, who was well known in the area, in fact, I was just remembering taking a walk with him out there somewhere in 2003. It's his fault. So the idea is, but see, the thing is, it was so sleazy. If you were aware of the press, right, it was so cheap. The people like hats with Einstein's head and stuff, and it was just so kind of trashy. And but that was all deliberate. So Ludwig, back in like the mid '90s, that was entirely his goal. His whole goal was that he was just trying to bring publicity to the problem, and it worked. So I guess whatever. So that's another good lesson if you want. Just name your thing. They like the God formula or something, and you're set. And then just as a quick thing, I just want to point out that there were many other sort of attempted examples. So this is something that's became to be called weakly aperiodic, which is this tile from 93 or so. Well, the first version was from 88 and then the 93 or so. Is this weird thing? It has these roofs. It's a pair of roofs stuck together, but at an irrational angle. And so you can layer these guys up. The upside down roofs of this layer fit into those of that layer, but everything is turned by an irrational angle from layer to layer. And so there's no compact, there's no group that has a compact quotient that acts on this thing. There's no finite fundamental domain, but it definitely allows, and believe it or not, it has uncountably many tilings, which you can quickly satisfy yourself of, but countably many of them have a corkscrew motion. They're invariant under a corkscrew motion. And so what emerged was this idea that, okay, we have weakly aperiodic things. They don't have compact quotients, tilings with compact quotients, but they do possibly allow some lower rank symmetry. And so this was kind of a problematic example. Another problematic example is this one, which I've mentioned before. So, no, I didn't. I don't know why there's this lag. It's so strange. Okay, so in any case, this thing I mentioned before, is weakly aperiodic. It has no compact quotient, but it does admit tilings with an infinite cyclic action. Namely, you could just translate up and down this thing. Or if you prefer, if you're not comfortable in the model, you could just simply dilate around that point, shrink by a factor of 2 around some point like that. And there's at least one of these. You could construct one where this line goes up forever, and then that would have a infinite cyclic action. And then, and it turns out to be kind of a generic thing. And then we also have to be careful about what we mean by the rules. So this is certainly, even the 2x1 rectangle is an aperiodic monotile, but in a very cheap way. So this was also problematic because people, as we'll see, could trade off, you can trade complexity where it's hiding. And so here you can have just a 2x1 rectangle as your tile, but you're hiding all the complexity in these very, very complex rules. The rules are like you have an atlas of what's allowed, and your atlas is you take basically your original set of tiles, say, marked up, and you just pixelate them. And then you divide the pixels up, and this is like the kind of thing that you allow. And you make these rules big enough so that basically if a 2x1 rectangle is in an appropriate, if every 2x1 rectangle is in an appropriate atlas, then the whole thing has to be, it's just going to do the same thing as the original Wang tiles. So that's cheap. That's not what we mean. And then we also have this situation that shingles may be aperiodic. So this is another thing that came out about 25, 30 years ago now, is the number of these where you can have overlapping tiles. A single overlapping tile remarkably can be aperiodic. And the most elegant and simplest example of this is just simply one of the Penrose kite, the inflated Penrose kite. If you allow it to overlap and you have rules, and it's really weird, they line up in a strange way with the, but that has to be non-periodic. So that's not what we mean. And then with 2009, we have this one where the tiles, there's a whole lot about this tiling. This particular tile could have its own literature in some respects. There's a number of papers on it, and it has a whole history too that's very prior to this. But the problem is that the rule for what has to match is that this like bump has to match that little bump, and there's this like sort of, you have to leap across a couple of tiles to accomplish that. And you can do this with multiple tiles. If you allow multiple tiles, you can just sort of build a tile that does that. But if you want to have a single tile in this way, that you just have to have these non-standard rules. And you can get around this in a number of ways. The tile's either not connected, or the rules aren't neighbor to neighbor, or you can make the tiles in 2 layers. But either way, no matter what, that's not really what we mean, I think. And then this is a more recent example that points to the ways that you can hide complexity in the matching rules. This is very similar to the previous example. It has these Sierpinski triangle-like structures, but the rules cannot be encoded by bumps, jigsaw puzzle type pieces. The rules are a little complicated, involving the way that these arrows can interact with each other. So all of that's to say that definitions matter a lot if we're trying to get things down to one. And so we, of course, know, the question, of course, is, well, how far down can we get it? It's a little anticlimactic because you know the answer. And the answer is, there's Dave Smith. So I think I didn't actually end up talking much about the hat, and I'm almost out of time, but I would like to just say, for all of you young people especially, I think it's really interesting that Dave is not a professional mathematician, and I believe kind of firmly that a professional mathematician could not have done this work. And the reason is, so it's not just that it's really cool that somebody outside of the mathematical community did this, but actually that the mathematical community, the way we're set up professionally, we could not have done this. And the reason we could not have done this is, would you have been so crazily foolish to have done it? Like, what he did was he sat there and he just, for fun, year after year, just was playing with individual tiles with no hope of anything except that he enjoyed doing it, right? So you see that that's not really, it's not just that it's neat that he came from outside of academia, perhaps it was necessary that he came from outside of academia, which is kind of sobering, honestly. And anyway, here's the other collaborators, Craig Kaplan and Joseph Myers, who, and just to say, I'm out of time, so I'm not going to say much more except one last thing, which is that the basic idea of the hat, proving that the hat tile works, is to show exactly, to follow Berger's proof, to show that that there's some sort of hierarchical structure that the hat tile has to enforce. Why? It's a miracle. It truly is. But just to finally say a couple of things. It's really astonishing that it actually enforces several different non-compatible substitution structures, and I'm going to talk about that in a couple of weeks. I think that's really a remarkable feature that we haven't seen before. And it's also remarkable that it enforces this substitution structure without any markings. It's just a single shape, just it doesn't have any, I mean, it's really bizarre, honestly. They're like the examples I showed you before had these elaborate systems to ensure that they behaved the way that they were supposed to behave. That wasn't the case. I think that's the sign. So that's it. Thank you. Oh, I have one last thing. Again, at lunch, I would like to invite you all to, or at least a few of you who can stand, like to come and help me build this Klein quartet.
So, any questions?
You mentioned that so the hat enforces completely different substitutive structures.
Yeah.
Are they not like still a bit related in a sense?
That's so honestly, it's a bit of a mystery to me. I know that some of them, I know that like two of them are very clearly related in that sense. When you line them up, there's a natural sense in which the structures match, you know. And the way I would put it more is that there's a natural sense in which you can write down strings of symbols associated with every tile. I call that addressing. It has different names. And then there might be a straight line machine of some kind, or a transducer or something that could convert addresses in one to addresses in another. I think that's, or maybe there's some, maybe it's Sophic down to something like that. I think that's certain. But it's not clear because they're not all compatible. It's sort of weird. So this is still to be determined, I think.
Other questions?
So the hat, the original hat, this one, you can basically see it as 3 parts of hexagons.
Yes, that's right.
And has it been written how you can encode it in a set, so not a single one, a set of hexagon tiles with
Yes,
local rules?
Absolutely. So I don't have a slide for that, but that's a very, very productive way to look at it. So really what's, I think, a more appropriate way to understand these is that they're, in this case, 8 different marked hexagons that by some miracle can all be geometrically rendered in the same way.
So
That's kind of, you know, yeah, sorry.
So the hat SFT is in DD as by default in the examples folder. I will show it today. It's probably not as good as how you are coding it, but still. Any questions?
It's a trivia question, really. Why did you call the hat, and why did you call the
great.
spectre the spectre?
Okay, so that's a great. The
spectre is a turtle.
I was the third author brought in. So Dave contacted Craig, and then they needed somebody from the inside of the field, so they contacted me, and then I was smart enough to suggest that we contact Joseph. So and by the time they got to me, they had already just called it the hat. And but then recently I was watching Craig give a presentation, and it became clear that their initial decision to call it the hat, they well, it looks like a shirt, but we're going to call it the hat. So whatever. And then the spectre, honestly, so Dave, as far as I can tell, it was just somehow it somehow started being called the spectre. I don't really know. And I should have mentioned, of course, the spectre is not require rotations. For mathematicians, I don't think that's, I mean, reflections, I don't think that's a big deal to us at all, but the physicists and biochemists and so forth freaked out, so we were lucky on that front.
But the spectre, if you allow reflection, admits periodic tilings.
That's exactly right. Yeah, so again, you know, Dave was outside of academia, but this is a very mathematical insight that was Dave's. And I think it's worth noting, you know, that, I mean, he beat us in that. So the idea is that with the spectre, it has more, there's this continuum of tiles that are all combinatorially equivalent, but there's 3 exceptional spots where things kind of become degenerate. And one of them is where all the edge lengths are the same, and it does allow more possibilities in a periodic tiling. But then the insight that Dave had was that if we just restrict it further, it would therefore have enough possible flexibility if we didn't allow reflections, and of course it did. But again, that's a miracle. There's no real reason to expect that.
So we have no more time for questions.
Yes.
Okay, nobody
And you
challenges me
you
on
can
this.
keep the wooden tiles, please. So.
Okay, let's thank the speaker again.